before we start our tutorial sessions tomorrow and day after tomorrow. We are planning the two tutorial sessions. One is on deep learning using the Verilog HDL, and then the deep learning using the SDSoC, that is the high level language C, C++ on the SoC. So those two tutorial sessions, it is important to have some background about the system on chip we are going to use for those sessions. So I have included this session. And also I would like to connect this session with the yesterday's third session where we discussed the multi-arm bandit algorithms, which are the online learning algorithms. And I'll briefly discuss how to implement those algorithms on the SoC and what are the challenges are there, and what are their practical applications of those algorithms. So these are the few things I would like to discuss it, and I'll try to keep it as short as possible. So if you have any questions, any queries, feel free to raise your hand or ask in the chat window. I'd always like to have the sessions as interactive as possible. So try to keep the questions. So whenever we have the students, we usually get a lot of questions, but with the faculty, I think I'll be happy to have as many questions as possible there. Okay, so the outline of the presentation. In this presentation, first thing I'd like to convince you that why there is a need of algorithms to architecture mapping, or why we need to map some of the algorithms on the hardware implementation. We have already have a couple of good sessions on the edge AI, where they have more or less convinced you that there is a need of mapping the algorithms on the hardware. Then I'll try to introduce you to the second term, which is the system on chip. What are the system on chip platforms available today in the market, which we can use in the educational institute, which are cost effective. I'll try to introduce them and what are the different features of those platforms. Then I'll introduce you about how to map any algorithms on the system on chip. So there are certain processes needs to follow. For example, you need to do the hardware software co-design. You need to make the hardware reconfigurable. Then why the reconfigurable hardware is needed. Then reconfigurable hardware itself is not sufficient. Why you need an intelligent and the reconfigurable hardware. So I'll try to introduce those terms to you and try my best to inform you about what are the importance of this architectures from the future application perspective. Then, as I discussed, the deep learning part will be covered in the next two sessions, tomorrow and day after tomorrow. So I'll try to limit myself to the discussion of the online learning algorithm, which are the multi-arm bandit algorithm, which we discussed yesterday, and how they can be mapped on the hardware. And then some preliminary results I'll show you. So I'd like to credit most of the work which I'm presenting here to my student Sai Santosh. He was our BTech student. Now he's doing his master's in the Texas. And so during his BTech, he has published his work in the multiple venues, ISCAS, transactions, TCAS, industrial informatics, and some of the work is still under review in the neural network and the learning system transaction. Also, if you are interested in this domain, if you want to extend this work, the detailed handout, source codes, and video tutorials are already available on our YouTube page as well as on the GitHub link. So all the things, source codes everything is available online. So in case you are interested in this domain. Okay. So as I mentioned in the outline, the first thing I need to convince you that why we need to map the algorithms to architecture, or especially why the edge architecture. So by looking at the slide, can someone tell me what this slide represent? What is being mentioned here in the slide? Any guess? Yes. Hello. Any guess?
Cloud computing revenue.
Cloud computing revenue. Okay. So what you are learning from what is happening?
The cloud computing industry is increasing
Exponentially. Okay. So you can see that here this link indicates it's something related to the cloud computing. On the here you can see that the market in billion US dollars. So you can see that there is a significant jump in the cloud computing. Okay. And any reason why it is happening? What was the reason for this jump? Any guess?
Computational power.
Okay,
High demand
computational
on
power.
computational power, and that's not usually available.
Okay, then
Availability of the
storage, good. So another reason is also we are using a lot of devices which are being sold as intelligent devices, but actually these are the dumb devices. So what you do is that these devices, what they do, they capture your signals, maybe some audio, video, or some kind of signals, and they blindly send these signals to the cloud where the actual decision making is happening, and then the corresponding decision is sent back to those devices. So those devices are being sold as intelligent devices, but they are actually dumb devices which just do the mostly the capturing of the data and send it to the cloud. And if you don't trust me, so you can go to the area where you don't have a good network connectivity. So for example, if you can go to the Ladakh or in the north region or northeast region where sometimes the connectivity or the cellular connection is not available, and if you try to use these devices, Alexa or other devices, they will not work. And I have seen a lot of video highlighting this issue. Especially now we have the cars where we are too much dependent on this Alexa and other things. And when we take these cars to such places, you will see that these devices don't work. Why? Because if the network connectivity is not there, these devices will not be able to send the data, and then you won't get the desired functionality. So you can see that with the large number of these devices being deployed in our house as IoT devices, there is a significant data is being captured and being sent to the cloud where your algorithms are implemented, and then from there the algorithms, the final decisions are taken and sent back to these devices. Okay, no doubt that over the last couple of years, the devices are becoming more and more intelligent because of the edge AI technology, as Daniel and Hemdat mentioned in the beginning. But still, there is a lot of things are sent to the clouds. And as we know that the cloud resources are limited, your data centers, they are the power hungry data centers. They are not environmentally friendly, and they are also computationally expensive. So there is a huge demand on how to make use of how to limit the data being sent to the data center. For example, here these are some of the calculations are made. For example, if each person queries 98 minutes a day. So for example, if you use your devices, those IoT devices 98 minutes per day, that means only with 1 million people, that is very few number of devices, your cloud needs to process 94 TB of data, and that's a huge data you need to process. So suppose we have the 3.8 billion people, and if they use only 3 minutes per day, then we need to storage 11 picobytes of data, and it's a huge data needs to be processed. And with the work from home culture, which is being still continue for the last 2 years, we are sitting at home, and that means these devices are being more and more, and that means the cloud, lot of data needs to be processed at the cloud. Now we are talking about the industry 4.0 and the lot of automations in the industry, vehicular networks. You can see that the more data will be captured and more will be sent to the clouds, and this is going to make the life more even further difficult. So in addition to the cloud, there are security as well as the environmental aspects. Data centers consume significant amount of electricity, Due to the cooling, data redundancy, quality of service requirement, you need to replicate the data at the multiple data centers so that your downtime is reduced. And you can look at the there are multiple multiple videos are there on the how the big companies like Yahoo, Google, Facebook, Microsoft, how they maintain their data centers. On YouTube, this is a very beautiful set of videos are there, and where the lot of focus was on how to improve the energy efficiency of the data center. So they try to build the data center at the north region where the temperature is low, or they will use it near to the sea region where they can use the sea water to for the cooling purposes. So you can see that a lot of things are being done to make the data centers environmental friendly. So if the prediction, as per the prediction, 20% of the global electricity consumption will be because of the data centers by 2025. So it's a huge data environmental factor. Another issue is that security aspects or the privacy aspects. So you will see that this intelligence, so-called intelligence devices are capturing your voice sample, some recognition sample, or some additional data, and they are being sent to the cloud. So you don't know what is happening with the data. That data might be being used for some other purposes also. And there are a lot of reports are being in the newspaper about how this data are being used. And with the lot of IoT devices, with the weak legal framework, especially in the India, this is a challenging part, how to maintain the privacy and the security of our data. Okay, so and also the cyber attacks or the attacks, IoT attacks is also an important issue which needs to be tackled, because these IoT devices can be manipulated so that they can you can put the attack on your cloud network itself, so that you will get a huge number of queries to the cloud and your network will go down. So that is also the another reason. And that is the reason that the people are trying to discuss about the trying to explore the decentralized intelligence, and where the term called the edge computing or the edge AI is being introduced. So it has been introduced for a long time, but the significance or the actual importance or the impact is being seen in the last few years. Edge computing is a much wider and general term compared to the edge AI, because computing includes anything other than the AI algorithms also. So the idea is that instead of having the entire artificial AI algorithms or the entire computing at the clouds, you distribute it through your network. So you distribute some at the edge devices, some at the gateway devices, and some of the cloud, so that you distribute it everything. So some of the tasks can be done efficiently only at the edge devices itself, so that you don't need to send the data back to the gateway or the cloud server. So this is the distributed wireless networks are being developed. So the same thing can be applied in the wireless network, robotics, and as we have discussed in the along with the cloud computing, there is additional requirement of the latency. For example, if you are now discussing about the 5G and the 6G, where we are talking about the remote surgery, in that case, your latency factor is also significant. So in those cases, it is not possible to send the entire data to cloud and take the decision making in the cloud. You need to make your network as fast as possible. So that means you need to make your edge devices as capable as possible. So that means there is a need of efficient implementation of the algorithms on the edge platforms. I'm not talking about just AI algorithms, any algorithms, you need to map it efficiently on the edge platforms. Okay, and these edge platforms can be your gateways or your base stations, or you can be your mobile phones or your IoT sensors, or any devices which has a limited resource capability. Okay, so I hope that now I have convinced you about the why there is a need of the mapping of algorithms to AI, mapping of algorithms to architectures. And along with these IoT networks, even in the wireless communication also, there is a significant discussion going on how to use the AI algorithms in the wireless physical layer. So if you see, these are some of the slide snapshot I have taken in the one of the meeting. 3GPP meeting has happened in the July 2021. 3GPP is the standard body which developed the standards for the 4G, 5G, and even in the 6G. So in the 3GPP release 18, you can see that the multiple companies, Qualcomm, China Academy of Telecommunication Technology, Intel, there were Ericsson, multiple companies were there. They are now started the discussion about whether it is possible to include the AI ML algorithms with the wireless physical layer. And if you want to include the AI algorithms in the wireless physical layer, first you need to, you can develop the AI ML algorithm for the physical layer, but as Danilo mentioned in his talk as well, that you need to make sure that these algorithms are, whatever you develop, these algorithms are works in the practice. It shouldn't happen that the data set what you use for the training and the data set in the reality is different. So that is the one challenge. And the second thing is that they are feasible on the hardware. So you need to do a lot of things to make sure that they are feasible on the hardware. You need to do the compression of the algorithms. You need to do the word length optimization. You need to look at what is your edge platform. It can be only microcontroller. It can be a microcontroller with the DSP processor. It can be microcontroller with the SIMD processor. It can be microcontroller with the floating point unit. It can be microcontroller with the GPU, or it can be microcontroller with the GPU or CKP. It's a combination of multiple things. So basically, you should be able to map your algorithms onto your edge platform, which may be of the with the different resources capability. For example, in the companies are talking about now replacing each model in our wireless physical layer with the deep learning model. In the future, there may be one model, their complete entire signal processing at the physical layer will be replaced by the neural network. So it may happen. The companies are only thinking about it. And the expected timeline, if you see, the expected timeline is that 5 years down the line, you will see that the physical layer is being completely replaced by the AI/ML algorithm. So these are the, again, research issues people are talking about, but that also highlights that the developing the ML algorithm is a one challenge, but also making them feasible on the hardware, making them work in the environmental condition is another challenge. So that's why the algorithm mapping of the algorithms on the architecture is important. So I hope now I have convinced that there is a need of algorithms to architecture mapping on the algorithms to architecture mapping is needed. Now we need to look at what are the platforms are available to do such mapping. So before I go to such system on chip platform, I would like to know if there are any queries from the audience, anything which is not clear, or everything is going fine. Okay. So it seems that there are no
everything
queries.
is going fine.
Yeah. Okay. Thank you. Thank you. Okay. So so now we need to look at the system on chip platform. So before we look at the system on chip platform, we need to understand what is the system on chip. Okay. So we have seen a lot of PCB boards where you have the multiple chips there on the system on chip system on board. So you can see that this one is the system on board. So which means you have one PCB board where you have multiple different systems or the chips, but they are externally connected. While the system on chip is that you have the single chip and all this functionality is embedded inside the system on chip, in a chip. So system on chip is like a more integrated version of the system on board. So system on chip is a single silicon chip that can be used to implement the functionality of the entire system rather than using the several different physical chips on the board. Okay. So for example, if you take the simple example of the system on chip, we can take it as a Bluetooth based microcontroller. So you may have the multiple chips in the market which supports the Bluetooth. For example, the headphone I'm using, it has the functionality of the audio signal processing to process my data, as well as it has the Bluetooth chip in between. So this you can design it either using the system on board where you have the one processor chip, one audio chip, and then one Bluetooth chip. or you can design it using the system on chip SoC, where you have a single chip where entire thing is Bluetooth, audio processing, any interfaces. For example, there is a USB-C interface for the charging. Everything is interface on a single chip. So either you can use the single chip or you can use the system on board. And you can see that if you see the evolution of our headphone for the last 10 years, they are getting smaller and smaller. Now, instead of having the wire, now I can have the small one like earbuds or earpods, and with the same functionality they provide. Okay, obviously they sometimes connectivity is an issue, but you will see that that will overcome in the next couple of years. So what are the advantages when you go from the system on board to the system on chip? Your design becomes small. You get the higher performance benefiting from the less propagation delay. So you can see that in case of the system on board, you will have the multiple chips which are connected to each other via external interface. So you can see that the propagation delay is much higher in the system on board compared to the system on chip. So your performance will be better. Also, the gate delay will be higher because your distance and your circuit is smaller. Then, if you are from the VLSI background, you might know that if you want to drive the signal outside the chip, the voltage requirement is higher than the when you want to drive the signal inside the chip. So you can see that in case of the system on chip, the power consumption will be less compared to the system on board. And the lower capacitance is also the advantage, which will take the less current to drive the capacitor. Then size is small. We have the examples of the Bluetooth. We have the example of your mobile phone. The size is getting smaller and smaller. The reliability is better. You can see that with respect to the wired headphone, sometimes they may still give the better performance, but now we are moving away from the wired headphone, because you can see that in the wired headphone, you can't move around during your talk. Second is that if the wire breaks, then the headphone goes away. So there is a reliability issues are there. So those are the issues are there in case of the headphone. Then if you go to the more complex application, you will see that there are certain security issues are there. If you are in the system on chip, it is very difficult to go inside the chip and track your signal compared to the system on board, where the signal is going outside the chip, so you can easily track it. So that is issue. Then interference is also another issue where system on chip offers the better performance. And the cost is significantly less, because you are, instead of fabricating multiple chips, you are fabricating only one chip. So that means the fabrication, usually the cost is less. So these are the advantages of the system on chip. But you might be wondering why I'm talking about all these things, because system on chip is already there in the market. It is well mature technology and everybody knows about it. So then why we are talking about in this workshop? But there are certain limitations of the system on chip. And I would like to know, can you tell me any of the limitation? Do you find any limitation of the system on chip, which you think that, okay, this should be addressed in the future? Any guess, random guess?
Memory bandwidth.
Memory bandwidth means you can say that once the system on chip is fabricated, you can't add additional memory.
Yeah.
Yeah, good.
And it is quite rigid. You can't change the functionality.
Yes.
Or anything.
Yes, exactly. So once you fabricate it, like for example, if they support the current Bluetooth, if in the new future new Bluetooth comes, it will not support.
Yeah. In case of board, we can replace the
yes,
items
exactly.
like that.
Exactly.
Yeah.
Good. So I think that whatever I want to convey is being conveyed. So that's a good thing. So as we mentioned that the system on chip has the issue with the less flexibility. For example, if you look at our laptop or the desktop, suppose while buying the laptop, if you buy the laptop with the 4 GB RAM and then we want to increase the RAM further, suppose 16 GB, you know that you can, as long as there is a port is there, you can add the additional RAM. This is not possible in system on chip because everything is incorporated inside the system on chip, so you can't change the memory. You can add the external memory, but that doesn't remain. Then it is no longer a system on chip. It becomes a system on board. Same case is the graphics card. So external components can be added, but it is no longer SoC. It's application specific. So most of the SoC, if you use, they are created for the particular application. For example, this SoC is being used for the headphone. There will be separate SoC for the earbud. There will be a separate SoC for, say, your FM radio. I don't know whether you remember, but if you remember around 2002 to 2010 period, we used to buy a separate FM unit. We didn't have the mobile phones with the FM integrated. We used to buy a separate mobile phones and the separate FM unit. But now it is no longer there. Now everything is integrated. But you can see that FM unit cannot be used for any other purpose. It can be used only to capture the FM signal. So these are the application specific integrated circuits. So that issue we need to sort it. And the complexity. So if you see that someone who is working on the system on board, suppose you are having your research lab or you are having your startup, and if you want to develop, suppose, this headphone, you can hire 3 engineers, 1 engineer for the audio processing, 1 engineer for the Bluetooth, and 1 engineer to take care of the entire chip, and that is fine. But now with the system on chip, you need to have the engineer which know everything, because it's all the 3 things are implemented inside the single chip. So you need to have the manpower which has the advanced skills compared to the board level development, and that has become one challenge. And that's why the VLSI people who are working in the VLSI domain, they are now living in the golden era, because you can see that the packages and the kind of work quality they are getting, even in the India, it is equivalent to the software engineer. So and the challenges is that because this design is very complex, testing is also even more complex of the SoC. So these are the complex which are there even today industries are facing. Any other things like you want to see in the future perspective, like next 5 years, you think that, okay, this problem needs to be solved in the system on chip? Anything you think that, okay, this is the problem I want to be solved from the system on chip domain? Or in your mobile phone, are you facing any problem which you think that, okay, this should be sorted out? Okay, so now I'll tell you. So now what I'm yes. So
I want to add one thing, just
Yeah.
what you're discussing.
Yeah.
One more thing,
Yeah.
that in case of the system on chip, okay, because it is very rigid, we can't change any functionality.
Yeah.
And the NRE cost, the non-recurring engineering cost, is very high.
Yes.
So if the volume is low,
Yes.
then it would be very expensive.
Exactly. So I think you know all my slides in the future.
No. I don't know your slide. Actually, my
joking.
area of research is also custom processor
Okay,
design.
great. So
I have worked in IIIT Delhi.
Okay.
Professor Bala and Anshul.
Yes. Great. So I was just joking. So yeah. So you can see that over the last 10-20 years, because I take only that example, over the last 10-20 years, what was our expectation? So if you take the mobile as our example, what was our expectation? That we should get as many functionality as possible in our single SoC. That was our requirement, and we wanted our battery of your mobile phones to be as longer as possible. Our touchscreen display should be as smooth as possible. Touchscreen should be as bright, as dynamic as possible. And you can see that the cost should be as low as possible. And you can see that our VLSI industry have been able to meet this requirement quite efficiently. We are very lucky to have the strong VLSI industry as well as the software industry also, to get our electronic products which are quite advanced, and sometimes they are so much advanced that they are giving us the features which even sometimes we don't want. So sometimes I wonder why we are using this wearable watch. So it looks very fancy, but I don't think means that actually is it's an important requirement. But you can see that the VLSI industry is so much advanced. We are getting the things which are, in terms of the functionality, they are much more better, and even sometimes they are not even requirement. So that is true. But these challenges have been addressed efficiently, that is fine, but the time is changing. Our user as well as the VLSI designer or engineer, their requirements are changing. One thing they are asking is the flexibility, and the second thing is the scalability. And these are the two requirements which are being put forth by the consumer as well as the VLSI engineer towards the VLSI or the software industry to solve this problem. Now look at the flexibility first. So for example, when you look at the 3G, 4G, 5G mobiles, you can see that the every time we go from the 3G to 4G, we need to buy a new mobile. Whenever we go from the 4G to 5G, we need to buy a new mobile. Or suppose, as I told you from the this headphone, suppose if you want to add the additional features, I will have to change my headphone. Okay, so people are now expecting that they need to have the flexible as well as reconfigurable hardware. That okay, even if I want to make my hardware, even if I purchase the hardware today, and in the future, if something new comes up, there should be a way to reconfigure my hardware to meet the future requirement. Okay, so for example, if I buy my mobile phone today, and if it is doesn't support, if it is not supporting the 5G, and if the 5G comes in the next 2 years, why I need to replace the entire mobile phone? Can the some part of the mobile phone to be replaced to support the 5G? Okay, so this is a very advanced use case. It won't happen in 10 years, but at least people are starting discussing all those things. Second thing is the scalability. For example, you are a VLSI engineer. Suppose you are working in a industry. I'll again take the example of the headphone. You are developing the headphone, and you are developing two types of headphone. One is the low-end headphone, which cost around say 2,000. It's not a low-end, but say like 2,000 rupees, and another high-end headphone which costs around 10,000 rupees. And you can see that the difference between the two headphones will be the quality of the sound, the features which are supported. Now, if you are a VLSI engineer or some the architect in the company, and your boss tells you that okay, for the low-end headphone you should use say this X processor or X product from the chips from the company X, and for a high-end processor you should use the chips from the company Y. Now, as a designer, what are your challenges? You need to learn the architecture about the X as well as the Y. You need to develop the code which will be efficiently mapped to the X, as well as you need to modify your code which will be efficiently mapped to the Y. And you can see that that's a lot of work, developing, understanding algorithms, understanding architecture and mapping. So that's a lot of work. So the VLSI designers are also fed up with this one, and they are asking the VLSI industry to come up with the platform which is scalable. What do you mean by scalable? That the same platform can be used for the low-end devices as well as high-end devices. The architecture remains the same, but the resources can vary. For example, in the low-end devices, you can use the single-core processor. For the high-end devices, you can use the quad-core processor. In the low-end devices, you may not use the GPU. For high-end devices, you may use the small GPU. So, but the architecture remains the same. Once you understand the processor architecture, it is just a matter of time to include the number of cores, number of co-processor. That is not a challenge. But if the processor architecture itself is a difficult, then that's an issue. And now the industry is trying to focus on how to address this flexibility and the scalability one. And few of the things are being proposed in the industry and which are getting more popular in the today's educational industry as well as academia. So you can see that you have the initially you had only the processor. Nowadays you have your mobile phone is GPU is a part of your processor system, so it's you can't have the processor without the GPU, and you can have the hardware, say ASIC or the FPGA, to accelerate the certain task, because processor and the GPU are still a sequential unit, but by using the ASIC or FPGA, you can accelerate the task. And the difference between the ASIC and the FPGA, you can see that the ASIC are the application-specific integrated circuit, and the FPGA are the field programmable gate array. So in the case of the ASIC, once you fabricate the thing, you can't change the algorithm. While in case of the FPGA, even if you deliver your product to the customer, you can change the algorithm. For example, if you deliver this product to the customer and then in the future customer wants to add some changes in the algorithm, or you want to change the filter which is used for the audio signal processing. In case of the ASIC, you can't change it, but in case of the FPGA, you can change. Again, there are multiple drawbacks of the FPGAs and all. So right now we don't have time to discuss this one, but I'll share the resources if you want to know more about this one. But you can see that this is still a system on board. You can have the external chip, and there are all the issues of the system on board will be there in this system. So then the people came up with this system on chip, where what they did, they have the single chip, and there they had the hard processor, which is this is the PowerPC processor from the IBM, which was one of the popular processor a few years back, maybe 15-20 years back. What they did, they developed a single chip where you have the FPGA or ASIC hardware as well as the processor on the same chip. So you can see that the issues about the external links have been addressed here. Then over the time, you know that the ARM became more popular. ARM processors were quite efficient. So what they did, they replaced this PowerPC processor with the ARM dual core processor. This is the Cortex A9 processor. And this architecture, if you are familiar in the FPGA or the Xilinx or the Intel architectures, this is a Zinc architecture. So this Zinc architecture, you can see that it's a SoC. It is called as the AP SoC, which is the all programmable SoC, where you can see that it's a dual core ARM processor. So this is the ARM processor, dual core processor, and this is the FPGA, which is the 7 series FPGA. Okay. So Sudipta, I'll repeat this in a minute. Okay. So then you can see that they extended this architecture further. Here you can see that instead of having the dual core, there is a quad core processor, but the rest of the architecture remains the same. Then they added the GPU there, they added the real-time processor for the embedded application. Then they added the additional unit as per the unit, like you need a floating point unit, you need a SIMD processor. So these are the things they have added. Then similarly, you know that in the FPGA there were two companies. One is the Xilinx and the second was Altera. And you might be aware that the Altera was bought by the Intel, and recently Xilinx is now is getting merged with the AMD, which is the two processor company. So you will see that in the future FPGA will be part of the processing system as well. So similarly, the Intel also has come up with the similar system on chip. Then in the morning we saw about the STM. They are also coming with the system on chip board for the AI application. Then from the NVIDIA, they are also coming with the system on chip. And recently in the Xilinx for the 5G applications, they have extended this MP-SoC to the RF-SoC, where along with this systems, they are also having the ADCs and the DSCs on the single chip. So everything is on one chip. You have the processor, you have the FPGA, you have the GPU, you have the ADC, DSC, everything is on a single chip. And here I'm talking about the scalable architectures. So you can see that once you understand the processor architecture, once you understand the FPGA architecture, you can easily switch between any of these two. So that is called as a scalable architecture. And this is also called as a heterogeneous architecture, because in a single chip, you have the processor, which is the sequential. You have the FPGA, which is the parallel processing, which can accelerate the task. Then you have the GPU, you have the real-time processor, you have the floating point unit, you have everything on a single chip. And so that's why they are called as a heterogeneous system on chip. Okay, so these are the different platforms are available. In the future, you will see the more and more evolution of this platform. More and more platform will be available. But these are the platforms are being used for the mapping your algorithms to architecture. So Sudipta, which part you want me to repeat? Okay, I'll repeat it. So you can see that in the beginning we started with the processor architecture. So we had the simple processor, maybe dual core or the quad core processor, but later now to accelerate the task, we added the GPU. So if you see your mobile phones, you can see that now in the mobile phones, you can't have the mobile phones without the GPU. So mobile phones are the integrated part of the GPU. Then if you want to accelerate the task, for example, if you want to use for the computer vision application, base station in the mobile tower application, you need to do the task which can be parallelized in the significant manner. For example, FFT operation. FFT operation can be done in a parallel way, in much faster way than the processor or the GPU, where it's still a sequential unit. So then what they are adding, they have added the additional ASIC or the FPGA to augment your processor to perform certain tasks in much better way. So ASIC is the application specific integrated circuit, FPGA is the field programmable gate array. Both of them help us to accelerate the task, but ASIC is the application specific. So it is designed for one particular application, while FPGA can be reconfigured multiple times. So even if you deliver your product to the customer, you can reconfigure the architecture to add the future algorithm. So that's why the FPGAs are getting more popular. But here you can see that these are the external chips. So all the problems we discuss about the system on board are applicable here. And from here, they move to the system on chip, where in the system on chip, on a single chip, you have the processor, you have the ASIC on FPGA. Here, in the beginning, they use this PowerPC, which is the IBM processor, and later they moved on to the ARM processor. I hope this is clear now. Any other question? Is this clear? What are the architectures about the system on chip? Different architectures are available?
Yes.
Okay. Okay, so now we discuss about the need of the algorithms to architecture mapping. We discuss about what are the platforms are available. And now for the sake of this session, I'll focus on this. I'll focus on these architectures, how to map any algorithms on this architecture. For this architecture, in the morning, I have already shared the video. If you want to look at this one, you can share the video. Right now, we don't have this architecture, so I don't have much idea about how to map it. But this and this should be same, because they are almost, the architecture is identical, the Intel FPGA or the Xilinx FPGA. So now we'll move to how the algorithms to architecture mapping is done. Okay, so as I told you, you have the algorithms which will consist of the multiple sub algorithms or multiple sub blocks. For example, this is my algorithm where you have the multiple operations to be done before I get the output. Now I want to implement this algorithm on the system on chip, which is this my system on chip, where I have the dual core ARM processor. I have the on the ARM processor, I have the co-processor which can do the SIMD, that is single instruction multiple data, or floating point unit which can do the floating point operation, and also have the yellow color part which is the programmable logic, which also call it as a FPGA. Now how I'll decide which part of my algorithms will be mapped to the FPGA and which part of my algorithms will be mapped on the processor. Any idea, any guess? If I ask you to do it, how you will decide? How you will take the decision, like which part to be implemented on FPGA and which part on the
Can I speak?
processor? Yeah.
So actually, we have to find the computation intensive parts of the application, which are consuming most of the execution time. And that should be targeted to transfer into hardware. So basically, we will transfer that functionality into FPGA. Okay, so now in the code design phase, rather than running everything on our system, we would like to interface the design we are doing for that functionality, and we will not run that code into our system.
So one thing is that whatever is the complexity part, complex part will move to the FPGA, right? Second is that the control path on the processor, and I'm happy to see this answer. Good. So second part is that usually your systems can be differentiated into the data path and the control path. So the data path is usually goes to the PL in most of the case, and the control path goes to the PS. Very good. So that is the PS. Okay, so sequential instruction on the processor, parallel, yeah. So whatever the complex, when you say, if it is possible to parallelize it, you can move to the PL. Good. Any other thing? So if everything is know what I'm doing, so I need to find out something new I should contribute. So I think I have something new which is not yet been answered. Anything else? Any other design you will make? Okay, so that means I have something new to share today. So you can see that the first part when you talk about the heterogeneous SoC is that you need to do the hardware software co-design. What do you mean by hardware software co-design? You need to decide which part of the things will go on the FPGA, which part of the things will go on the processing system. And now you may have the complex SoC where you have real-time processor, you have the GPU, you have the floating point unit inside the FPGA, you have the multiple subcomponents. So you need to decide which part goes to the which part unit to meet the user requirement and the constraint. For example, sometimes user have the cost constraint, and in that case, using the FPGA may not make any sense. So you can just tell that, okay, everything will be implemented inside the PS. I will not use the FPGA, and that will. Sometimes user want a very high speed, like load latency. So in that case, you can tell the user that if you use the PL, you can make the use of the PL to get the better performance, but it will be slightly more expensive or more power consumption. Sometimes user may need a future upgradation. So in the future upgradation cannot be possible, future upgradation and the low latency cannot be possible without using the FPGA. So it is all based upon, you need to understand the user requirement, you need to understand the user constraint, and then you need to choose the architecture. You can't blindly use the one architecture everywhere. You need to choose the architecture as per the user requirement. So the first thing in the SoC is the hardware software co-design. You need to profile your architecture. You need to decide, you need to try out the different combinations, and you need to decide which part of your algorithms will go into the which unit of this one. And again, it comes with the experience. It comes with, there are certain tools are there, but the tools has their own limitation. It is more of an experience and understanding the user requirement that will help you to do the hardware software co-design. For example, in the deep learning algorithm, there are multiple examples you can consider. You have the different layers. You need to decide the which layer goes to the where. For example, in the we have the tutorials on the 4th and the 5th day where we'll discuss the how to map the convolution network layer on the FPGA and how to make keep your fully connected layer on the processor itself. And the video is already available. I have given the link also. So we have shown the result, like there is no point in moving the fully connected to the FPGA. You should keep it on the convolution. You should keep it on the PS itself. So these are all the things you will do it only on after only analyzing your code. So this is the hardware software co-design, and that is very well known in the industry as well as academia. Many people knows. And if you want to also, whenever you want to design something on the hardware like FPGA, you need to write a code in the HDL language, Verilog VHDL, or high level you need to use the C++ language, or use the HLS tool, high level synthesis tool, which converts your C++ code into the Verilog code. So that is the part which you want to implement on the PS. Whatever you want to implement on the PS, there are different approaches. You can first deploy the operating system on the PS and then write an appropriate application for that operating system. Or you can do the bare metal code. You can write a normal C++ code, or even in the Python code, and you can implement your algorithm on the PS. So there are multiple ways are there to do the mappings there. But you can see that it's a complex steps are there, and you need to understand the different processes. But what I want to look into the thing is that hardware software co-design will reach you to the one step only. But if you go back to the requirement I mentioned in the beginning, I mentioned the two requirements, flexibility and the scalability. I'll request Aparna to mute your mic because it's a lot of disturbance from your end. So you can see that there are two requirements from the customers and the designer. One was the scalability and the flexibility. The scalability requirement is being addressed by the VLSI industry, and the flexibility requirement as a designer, you need to address, and then you need to address is by using the tools. For example, by using the FPGA, FPGA are the field programmable gate array. So you can change the functionality of the some part of the FPGA or full part of the FPGA by reconfiguring it with a new file. So for example, in case of the computer vision algorithm, you are aware that the some algorithms works well in the morning, some algorithms work well in the night, and the some algorithms works well in the evening. Do you want to implement all the three algorithms in your product and then deliver it to the customer? Then that product will be bulky. It will have a lot of power consumption. It will be costly also. But if someone tells me that, okay, you have this reconfigurable architecture where you can configure the same part of your algorithms with the different versions of your algorithms without need of implementing three algorithms in parallel. And this is called the reconfigurable architecture. So when you take this hardware software co-design decision, which part to be implemented in the hardware and which part in this one, you, in addition to the complexity, you need to also look into the what is the reconfigurability requirement in the future, whether this part, if if I implement in the FPGA, should I implement in the FPGA, is there any reconfigurability requirement or future upgradation requirement? That also will be the one of the things you need to look into the aspects while taking the hardware software co-design. Okay, so by using the reconfigurable architecture, obviously your power consumption will be less, because instead of having the three algorithms in parallel, you will have only one algorithm which is active at a time. Your resource requirement will be less. Also, you can see that the FPGAs are till now today are expensive. So if you implement three algorithms in parallel, that means you need to use the larger FPGA. But by using the one algorithm, which one architecture, reconfigurable architecture, which can switch between the algorithm, you can see that your size of the FPGA can be reduced and your power consumption as well as the cost can be reduced. So these are the advantages are there because of the reconfigurable architecture. But is the reconfigurable is the one another advantage is that the feature richness and upgradability. For example, your customer came up with the requirement X1, X2, X3, and you develop the product and deliver it to the customer. Now, after say 5-6 months, customers say that, okay, this is the X4 is the additional requirement. Can it be included in the product? If you are using such a reconfigurable architecture, why not? You can always design the algorithms. You can develop the corresponding hardware file, remotely deliver it to the customer, and the customer will get the additional features. You will get a customer satisfaction. You will get more money, and customer doesn't need to recall the product and refabricate the chip. You can customer can keep on adding the new features in your hardware as long as the resources are sufficient. So you will get the product which is feature richness and the upgradability. Like in the future, if you want to upgrade your product, that is also possible. And that is the reason the FPGAs are getting more and more popular. So if you see the very typical example of the 4G and 5G. 4G in India has happened in the 2016. And you can see that in all over the India, all over the world, 5G is already deployed. The initial version of the 5G is already deployed in 3.5 gigahertz band. It's at the core network is 4G, but their network support the 5G mobile phones. But India, it's not there. One thing people can complain that, okay, this is because the government has not auctioned the spectrum and other things. But the another important issue is the cost. The 4G service operator has invested so much amount of money. So and all those mobile towers were ASIC based mobile towers. And now if they want to replace with the 5G, they need to replace all those hardwares with the new 5G hardware. And you will see that the 5G is much more advanced, and you will see that in the next, they are saying that 2022, the 5G will be deployed, but that is just one version of the 5G. At the core network, it's a 4G, and there will be future 5.1G, 5.2G over the next 5 to 6 years. So you don't want your service operator to keep on replacing their hardware. So what they are trying to do, they're trying to make use of the FPGA so that even at the future upgradation, if possible, you can do it remotely. And since the number of base stations are going to be relatively smaller in number, FPGA will be cost effective compared to the ASIC based system. So that is the advantage where the FPGAs are getting popular. But designing the reconfigurable architecture itself is not sufficient. Suppose I gave you the algorithm that, okay, this algorithm works in the morning time, this algorithm works in the evening time, this is the night time. But do you need an intelligence to sense your environment and then reconfigure your hardware? Because you can't do it manually. You need to have the intelligence which will sense your environment. For example, in case of the wireless one, you need to sense your RF spectrum, understand, learn the parameters, and then change your adapt your algorithms as well. So that means you need an intelligence for the reconfigurable. So reconfigurable architecture itself is not sufficient. You need an intelligence to make use of the reconfigurable architecture. And this we call it as a intelligent reconfigurable architecture, where by using the FPGA or using the processor, we make it reconfigurable, but we need to add the intelligence to make the algorithm adaptive, or it can adapt in the unknown environment. For example, in the robotics, in case of the wireless communication, you need to make sure that you learn from the environment and adapt your parameters as per the environment. And just learning is not sufficient. You need to learn, but you need to also learn to forget and relearn, because your environment will keep on changing. So you need to learn, then you will forget, then you need to understand when to forget, then when to relearn. So these are the challenges which need to be sorted out. For example, in the yesterday's session, there was one question on the stationarity and the non-stationarity. So, and that is true question, right? You need to understand that, okay, when your environment is stationary, you are going to learn. But when the environment is non-stationary, whatever you are going to learn, it will become ineffective after a certain time. So you need to learn to forget and relearn. So that is also important, that your algorithm should take into these aspects. Okay, so this intelligent reconfigurable hardware software design, you can apply the same concept to the deep learning. You can apply the same concept to the wireless communication. I work in these two domains, so I know this one, but there will be multiple other applications. Concept remains same. Basically, you should have the good understanding about the algorithms, good understanding about the architecture, good understanding about the platform you are implemented, good understanding about what are the goals you need to achieve in terms of the cost, power, and then the good hands-on programmability capabilities, so that you can make your algorithm works on the hardware. Okay, so this completes my third session, where I hope I have convinced you about what is the need of the intelligent reconfigurable hardware software co-design. If you have any question, feel free to ask me, and then I'll just focus on mapping the multi-arm bandage algorithms on the hardware. I'll give you the brief session on that, which we also use it for the decision making. So if there are any questions, feel free to ask me now.
I have a curiosity, not basic question, just discussion. So we are saying reconfigurable hardware, and then we want to move to the intelligent reconfigurable hardware.
Yeah.
Okay. So what I was trying to think is, at the design point of design time, we use the FPGA for prototyping.
Yes.
Okay.
Yes.
But when we deploy the product in the market, I think we have to go in the chip.
Yes. Yeah.
So in the chip, how would we make intelligent?
Yeah. Very good question. Yeah, very good question. So again, that's why I was giving the example of the 4G to 5G one. Yeah. So you can see that if you are going to develop your product in case of the like in the millions of volumes. So in the today's one, there is no alternative to the ASIC. Okay. So whatever the reconfigurability you need to do it at the processor level or the GPU level. Yes. The ASIC part will be fixed. But now, and the first question, as any student or this one, the FPGAs are used for the prototyping in the ASIC industry itself. Yes. But now there are multiple test cases are being developed where FPGAs are also being used in the direct product itself. So one is the your cellular tower. Second is your ADAS system, where you can use this FPGA. Third is your computer vision algorithms, because your product lifetime is very short nowadays.
But they would be very expensive. No?
Yes, so that's the thing, and that's the reason you can see that these big companies have now acquired the AMD has acquired the Xilinx, and the Intel has acquired the Cadence. So there is no these are with this acquisition and with the more things, more development at the architecture level, hopefully the cost will go down. And another thing is we can't compare with the ASIC in the FPGA because the requirement is there. In the ASIC, you can't
Yes.
ask for the future upgradation.
Yes.
In the FPGA, you can ask for the future upgradation. So it is like a two kind of products are being developed, and depending upon what customer wants, they will look. So if the customer wants that, okay, this is the product I want to use it with, I don't want a future upgradability, okay, this is the one. But
Yes.
here the customer wants future one, then this will be the case one. Like for example, the service operator, the cellular one, they are now going to the at least in the complete hardware from the 100% ASIC, they are at least going to the 50% FPGA and 50% ASIC. So it is all the application one, but anyone who learns to develop the algorithms for the FPGA will be able to do it for the ASIC as well, because till the RTL part, it remains the same.
Yes.
So as a student, that's, and also in the academia, the important part is the academia. We can't have the hands-on session on the ASIC in the academy. It is way above our budget, and also in the course we can't do it. In the FPGA, I start with the morning lab. Within the 3 hours lab, my student can develop the algorithms and test it on the hardware. So in the education institute, we don't have the replacement for that right now.
Yes. Thank you very much.
Yeah. So is there any problem?
Excellent session. Thank you very much.
Thank you. Thank you.
Yeah.
So is there any problem? Just one question was there. Is there any problem of switching transient in the reconfig? Yes, very good question. There will be transient will be there. Basically, you need to make sure that you are transient during the transient time. You don't you make sure that your output is disabled. That you need to take care. But whenever you switch from one algorithms to another, there will be certain transient will be there, and that you need to take. You should be aware about it, and you need to take care of it. Oh, BTech AIML. So I'll come back to that at the end. I'll come back to that BTech AIML. We have the a good set of video tutorials and all those things for at IIIT Delhi, and we have. I'll come back to that part. Okay. So now. Can the DL model training is okay? Yeah, that's a good question. Can the DL model training? So right now the focus is on the inference, but with the evolution of this federated learning, where you need to do the training at the edges as well as in the cloud, and it should be shared. We have to go to the training and the FPGA. There are certain papers are there in the last couple of years, but that will happen soon. Basically, it's not a challenge, because basically you need to learn about how the back propagation done, and on a large scale data set, a large scale one. And if that can be done, I don't see any challenge in doing the training on the FPGA itself. Yeah, so these are the different activation, because I think yesterday, if you see the first session where Saket told us about the sigmoid one, how they came up with the sigmoid, why they developed with the sigmoid. So similarly, there is a R, ReLU, CeLU, and the ReLU. These are the different activation functions which are used in the deep learning model. I'll have to pass this comment, and I think it is better to check with the person who works in the deep learning one to understand more about this. But these are the different activation functions. Basically, they introduce the non-linearity to get the desired functionality or the accuracy. Okay, so let's move to the multi-arm bandwidth algorithm, which we have discussed in the yesterday's one. And you can see that we discussed yesterday UCB algorithm, KL UCB algorithms and all. So I'd like to take, I need one volunteer so that I can explain this algorithm in the way which I want for the today's session. So any one of you can volunteer for this one. So you just need to take some decision based upon the scenario I give it. So anyone who wants to volunteer? Yes, no one wants to volunteer. Okay, yes. Sudipta, you can unmute yourself. So, as we discussed yesterday, right? We have this UCB algorithm. These UCB algorithms are the multi-arm-bandit algorithms which are used for the decision making. So these decision makings are the, like, suppose you have the multiple arms and you need to choose which arm to use. Suppose that we are applying this algorithm for wireless communication and you have the 3 channels, wireless channel, channel 1, channel 2 and channel 3. So you are the transmitter and you need to select which channel to choose. Each channel will give you the different throughput. So right now we'll make it the case simple that your data transmission is either successful or failure. Okay. You don't know about the channel. You don't know anything about the channel. You only know that the channel provides a throughput with a certain probability. And you need to select the channel which provide you as much throughput as possible. Okay. So now I'll give you the 10 chances. So one by one, you need to select the channel. You can use the chart window itself. You need to select the channel. And then I'll give you what throughput you have, whether your transmission is successful or not. And at the end of the certain time slot, you need to tell me which channel you think that is the good channel. Okay, let's take the 8 time slot. So in the beginning, which channel you will select? And I have the note written here, so I'll just look at that and will give you the answer 1 or 0. So I'm not going to manipulate the answer. So which channel you will select first?
Sir, at this point of time, we do not have a choice.
Yeah, so okay, you can go ahead. Which channel you will select? How you will solve this problem? Like how you will select the channel? Okay, first. So in the first, you got your transmission is successful, unsuccessful. So you got the 0 throughput. Now in the second time slot, what you will select? 2. Okay. So in the 2, you got successful, 1. In the third time slot, which one you will select? 2. You got 0. In the fourth time slot, what you will select? Animesh, 3. So fourth, you got 0. So in the fifth one, what you will select? There is no 4. There are only 3 channels are there. Okay. So wait. So I'll take 2. So 2 is the fifth. 2 you got 1. So in the sixth time slot, what will select? 2, 1, 2, 2. So 1 or 2? 2. Okay. Sixth time slot, you get 1. In the seventh time slot, which one you will select? 2. Seventh time slot, you will select 2. You got 1. In the eighth time slot, which one you will select? 2. You got 0. In the ninth time slot, which one you will select? 2. You got 0. Okay. So now you can see that what has happened. If you remember the yesterday lecture, Manjesh talked about the exploration and exploitation. So now you can see that if I want to give you the channel, I'll give channel information. This channel has got the success probability of 0.7. This channel has the success probability of 0.5, and this channel has the success probability of 0.1. So you can see that you are in the confusion state whether to select the channel 2 or channel 3 or channel 1. So what you did initially, you selected all the channels certain number of times, and then you suddenly realize, okay, channel 2 is giving me the good reward. So you got stuck at the channel 2. But in that time, you forget that, okay, you have not explored the channel 1 sufficient number of times. Okay. And this is called as a exploration. And this is very human kind of problem. Exploration, exploitation, trade-off. You don't know how much to explore. You don't know how much to exploit. You need to have the balance between the exploration and exploitation when you don't know this. And this is what the multi-arm bandit algorithm one. And yesterday Mansi explained about the UCB, KLUCB. You can come up with the multiple algorithms. But why these algorithms are popular? Because they have theoretically proven that they optimize this trade-off between the exploration and exploitation. So they optimize this trade-off, and that's why they are the popular algorithms. So they are theoretically proven. You can develop any heuristic algorithm, but you need to prove that your algorithm optimizes this trade-off, or it offers the logarithmic regret. Logarithmic regret means after certain time, you with certain guarantee, you will select the best channel. Okay, and the UCB is the one of the algorithms. So how the UCB works? In the UCB, the K are the number of arms. In the previous case, it was 3. N is the size, like how many times you are going to run the algorithm. Like in the previous case, we ran for the 9 time slot. IN is the algorithm arm or channel which you selected in the time slot N. And the RN is the received reward. In the previous case, you can see that you got the reward of 0 or 1, and you select the channel either 1, 2, or 3. And you can, what you do, you keep on adding the reward. If it is 1 or 0, you can keep on adding it to your particular channel history. And the T indicates the total number of times you have selected the particular channel. So X is the total reward you have received over the channel, and T is the total number of times you have received the channel. So what will be the X of T, X by T? So what will be the X by T? So X by T should be close to your actual mean of the channel, like with what probability it is giving the reward 1. Okay, so that is nothing but the X by T. Only thing is that we don't know the actual one, so it is the mu hat. That is, we are learning the what is the mean throughput of the each channel. Okay, so this is the mu hat which we are learning. So what this UCB algorithm does, in the first K time slot, you select the each arm once. That's what you also did. In the beginning, you selected the each arm once. Thereafter, what you do, you find out the quality factor for every arm based upon the information you have gained. Because when you are here, suppose you are here, you are using all this information to select the arm at this time. So this is what the UCB is doing. It is using all the previous information to select this arm. But what mistake you did? You didn't select this arm sufficient number of time. And how the UCB is avoiding this one? You can see that the UCB adding this T at the bottom. So when the T is small, that means your algorithm is not selected sufficient number of times. This term will become big, and then this term will become big, and then your algorithm will force you to select that algorithm, that arm, the arm which is not being selected. So this term is called as a exploitation term. What do you mean by exploitation term? That means you are selecting the arm which has the higher average mean, and this term is called as the exploration term. That means you are making sure that you have selected each arm sufficient number of time so that this is accurate. If you have not selected the arm sufficient number of time, this part is not accurate. Okay, and this is how the UCB optimizes the trade-off. And then once you find out the quality factor for every arm, you select the arm which has the highest quality factor, and you repeat this in every time slot. Okay, so similar to the UCB, there are other extension of the UCB, which is the UCB variance, UCB normal. There are multiple variants are there, but all of them try to, sometimes some try to learn mean, sometimes they try to learn the variance. So mapping these algorithms to the hardware, as Mansi explained yesterday, it is not that complex. But even if you take this as a case study, you can see that one thing you can implement entirely on the software. You get the flexibility, reconfigurability. By changing the C code, you can change the algorithm in the future always. And you can switch between the different version of the UCB as well. So that's not a problem. But on the software, the execution time will be very high. So what we do, we try to move some part of the algorithms to the hardware. So you can see that we have used the FPGA, PS, and PL. Some part of the algorithm is implemented on hardware. So this is UCB with the K is equal to 2 arms. I'll go faster because these are the architectural details. In case you want to know more, we have the resources available online. So you can see that by making these two things, you can see that for every arm, I need to do this calculation for every arm. If I do it on the processor, it will do it sequentially. If I do it on the FPGA, I can do them in parallel. So I'll get the speed up. Okay. Then sometimes I may have 2 channels, sometimes may have 3 channels, sometimes may have 4 channels. So how to do that? So you can see that I can make the reconfigurable architecture where I can switch between the channels. So this is called the reconfigurable UCB. So I can activate the different number of arms depending upon the user requirement. This is not the end. Like as I told you, I have the multiple algorithms. Sometimes I want to use UCB algorithm. Sometimes I want to use UCB V algorithm. Sometimes I want to use UCB T algorithm. Should I implement all the algorithms in parallel? No, I can use the reconfigurable capability of the FPGA. I can switch between the 3 algorithms. And this is called as the reconfigurable MMB. But so what is the advantage? I'll get the lower power consumption, smaller FPGA, and the better feature. I can, in the future, I can add the KLUCB, which Manjesh mentioned yesterday. This is not there today, but if the customer demands, in the future, I can add that algorithm also. So that is not possible with the ASIC. But what is the issue? We don't know which algorithm to choose at a particular time. So that intelligence part is still missing. But even with this feature, you can see that if I show you the few results, you can see that the blue one is the one where we implemented on the processor, and the orange one is the one where we implemented on the hardware, and you can get the significant improvement in the latency. And this is only with the 4 arms. So if you increase the number of arms, you will get the further improvement in the latency. So your execution time gets better, your resource utilization. If you implement Velcro by using the parallel implementation, by using the reconfigurable architecture, you will get the better resource utilization. So these are the advantages you get by using the hardware software co-design. Then when you move to the another advantage of the FPGA, which I forgot to mention, is that when you implement something on the ARM processor, on any software processor, you are limited by the word length of the corresponding processor. So you need to implement your architecture or all the arithmetic as 32-bit, 16-bit, or 8-bit. You don't have any flexibility. It is fixed by your processor architecture. But in the FPGA, I don't have any limitation. I can implement floating point. I can implement fixed point. I can implement integer arithmetic. I can implement 1-bit operation as well. So with the word length optimization, I can get significant reduction in the complexity. For example, you can see that here UCB blue color is implemented in floating point. So that is 32-bit floating point arithmetic, which is very expensive. And you can see that I have reduced the word length to 10 bits as well as 11 bits. So even if I reduce it to the 11 bits, I'm able to, my algorithm is able to identify the optimum arms, either 3, 8, or 4 correctly. So I can play around with the word length. And what is the advantage? By playing around with the word length, I can get the significant reduction in my resource utilization, power consumption, and the resource DSP. You can see that here I'm using the multipliers. With the reduction in the word length, I don't need to use the multiplier. So this is the advantage with the word length when you move something to the hardware. So you got a word length optimization. One more advantage, when you implement the Linux operating system on the processor, when you are doing multiple operations on the processor there, then you can see that by moving something to the hardware, you are freeing up your processor. That means your processor is free. So that means when there are certain important tasks, interrupts, processing, or certain emergency tasks are there, the processor remains free. Processor is not busy performing the other data processing tasks. So that advantage we get here. Okay. So this is the reconfigurable MAB algorithms where you can switch between the UCB and this one. Because of the limitation of the time, I won't discuss the other because we have the KLUCB algorithm and corresponding result. I can request you to go through the papers. So these are the advantages are there while mapping the algorithm. So you might say, okay, this is just mapping the algorithm. What is the research problem? So as I told you, I showed you only the UCB algorithm and KLUCB. There is another popular algorithm called as the Thompson sampling algorithm. And you will see that in the practice, it was developed in the 1933. And in the Yahoo search engine, it was deployed in the 1985. Yeah. So this is one of the popular algorithm, but there is no hardware FPGA compatibility of the algorithm. Why? Because this algorithm uses the beta distribution, and this beta distribution, okay, sorry, is very difficult to map it on the hardware. So then you need to put a lot of efforts to make this algorithm synthesizable. We have one research paper on this, but it is still under review. Then there are multiple variants of the algorithm. MEB algorithms are the basic algorithm. You need to go to the next version of this MEB algorithm. Most of them are not synthesizable. You need to add the intelligence. I have just discussed about how to select how to switch between the algorithm. But who will tell me which algorithm to select, which word length to select? You need to add the intelligence. You need to develop the algorithm. That is still yet open problem which we are discussing. Someone yesterday talked about the change stationarity. What happens when my channel which was good but becomes bad after some time? How I learn, how I forget, and how I relearn. So you need to add the change detection algorithm. Those we need to incorporate it here. So as I told you, hardware may not be hard, but it's a different. And the main problem we have is that we have the people who are very good in the theory, and some people we are very good in the hardware expert. But we need to have the combination of the both, where you need to understand the theory, you need to understand the architecture, and you should be able to take the theory, optimize it for the hardware, so that you can get the best result from the from your architecture or as per the user requirement. Okay, so this completes my discussion on the mapping the algorithms on the hardware. So I'll just take the couple of minutes. So as I told you in the morning, we have also worked on the deep learning and other algorithms, and there will be separate session on those. So I'm not going to cover. But this is in the morning we discuss about the STM and this one. So we have worked with the Danilo and all, and we have implemented the direction of arrival estimation on the microcontroller via neural network. And this demo is available even online, and there is a 1 hour tutorial available. And this got the best paper award recently. Then one of my students will be taking the session on the reconfigurable and intelligent architecture for the deep learning. Again, if you want to learn more, the video tutorial is available online if you want to learn more about the thing. But that tutorial session should be self-sufficient to understand this one. Our courses are, the lab part of our courses are online. So if you want to look at our courses and if you want to access to the lectures, you can contact me. I can share you the access. Lectures I have not made it online, but lab components we have made it online. And even in the online mode, where because of the COVID pandemic, we have make our labs also remotely accessible. So students are able to do their courses remotely, sitting at their home. They're able to program the FPGAs remotely. They are able to see the results on their desktop. So all the process is mentioned in the lab video. So if you want to know, please look at this. We also, during our courses, we have students work on the different projects. So they also develop the different video games on the FPGA by writing the complete Verilog code. So if you are interested, if you can have a look at those video tutorials. These are the games developed by the students by pure Verilog on the Basis 3 FPGA boards. So we also have the last 3 years we have started this 5-week program, which is, we call it as a VLSI revisited from analog to digital. So this is planned in the summer, just before the placement session. So in this 5-week, every week we cover the one particular topic in detail. It has the morning 3 hour, we have the theory session, and the evening 2 hours we have the tutorial session, hands-on session. So if you are students or if you are interested to take these sessions, it's a because again, if you want to get a job in the VLSI industry, having the deep understanding about these sessions is important. So in the last offering, we have 180 participants in the online mode in the June 2021, and industries are also using this as a platform to train their freshers. So if you are interested, feel free, please look at the corresponding advertisement, which will happen around April this year. And we are trying to go one step upward. This time we are targeting around 300 participants with the more kind of tutorial session. So if you are interested, or if your students are interested, feel free to connect with me for this one. Thank you very much. I took slightly extra time. If you have any questions, feel free to ask me. Otherwise, we are done for the today's session.
Thank you very much, sir.
Okay, thank you.